Okay, now we're going to go over section 2.8, which is the last section in chapter 2. It's about one-to-one functions and inverse functions. So let's define what we mean by one-to-one function. So a function, so if we're given a function, which means for every x there's exactly one y, it's said to be a one-to-one function, 1-1 function, if for every x in its domain there is exactly one y in the range, and vice versa. So for every x there must be exactly one y, and for every y there must be exactly one x. One-to-one. No x can be paired with two y's or more, and no y can be paired with two x or more. Algebraically, f is one-to-one if f of x1 equals f of x2. This automatically implies that x1 equals x2. If the y values are equal, then the x values are equal. Okay, for a function to be one-to-one, if I tell you that this function is one-to-one, and I give you this 5, 7, 3, 8, 11, 9. For this function to be one-to-one, it's missing two x values. If the y values are equal, then the x values must equal. So if this is a 1, then this must be what? A 1. Okay, that's the only way you can have a one-to-one function. If the y values are equal, then the x values are equal. Is this a one-to-one function? 1, 2, 3, 5, 7, 9. As long as no x is repeating and no y is repeating, okay, then it is a one-to-one function. If any x value is repeating, it's not even a function. If any y value is repeating, it's not a one-to-one function. So we use what we call the horizontal line test. Horizontal line test for testing a one-to-one function. A function f is one-to-one if no horizontal line intersects the graph of f more than once. If no horizontal line intersects the graph of f more than once. Number 10, page 226. 10, page 226. If you look at the graph, it's not one-to-one because part of it is a horizontal line. So if you draw a horizontal line here, it's going to cross the graph infinitely many times. So it's not one-to-one. Although it's a function, it is a vertical line test, it's not a one-to-one function. Because for one y value, you get so many x values, okay? If you look at 14, page 226, it says determine whether the function is one-to-one. 14, page 226. Apparently here they want us to do the algebra, so of course we can graph it, but algebraically this is one-to-one if the y values are equal. So given f of x1 equals f of x2, then we need to show that x1 equals 2. So if we put x1 in there, we get 3x1 minus 2 equal 3x2 minus 2. Add the 2. 3x1 equal 3x2. Divide by 3. So if the y values are equal, then the x values are equal. So f is one-to-one function. Of course, if we graph it, it's a line, so it passes the vertical line test and the horizontal line test. The vertical line test say it's a function, and the horizontal test to say it's a one-to-one function. Let's let 20. F of x equals x to the 4 plus 5, where x is between 0 and 2. So if f of x1 equals f of x2, then x1 to the 4 plus 5 equals x2 to the 4 plus 5. Subtract the 5, x2 to the 4. Now since x is positive between 0 and 2, when we do the fourth root, it's just going to be x1 equals x2, which makes it a one-to-one function. If x could be anything, then x1 would be x2 or the opposite of x2, and then it won't be a one-to-one function. If you graph it on that interval, just to get an idea, at 0 we are 5, at 1 we are at 6, and at 2 to the 4 is 16 plus 5 is 21, so somewhere there. So that's the graph. You can see it is a one-to-one. If we continue the graph, it won't be one-to-one. That's why they restricted the domain. Okay. So now we know what a one-to-one function should be. The inverse of a function. The inverse of a function. I'm going to introduce the inverse with an example. So if I have two functions, f of x equals 3x and g of x. So f times the input by 3, g is going to reverse that, dividing the input by 3. If you pick few values, like when x is 1, 3 times 1 is 3, when x is 2, 3 times 2 is 6, when x is 3, that's 9, when x is 4, 3 times 4 is 12, when x is 5, 3 times 5 is 15, and there's a million more, but that's enough. Now on the other hand, if I pick values for g, 3 for x, 1 for y, 6 for x, 2 for y, 9 for x, 3 for y, you can see how that works. 12 over 3 is 4, and then 15 over 3 is 5. You can see that if you compare f and g, domain of f, if it's only these points, it's 1, 2, 3, 4, 5, which is exactly the range of g, 1, 2, 3, 4, 5. Range of g, x is y, and then range of f, which is y, equal domain of g, which is x. So basically the concept of inverse is switching x and y. Switching x and y. Any two functions where x is y and y is x, domain range and range is domain, and not only that, if you do f of gx, nothing changes. Look, f of g of x is what? X over 3. If you plug this to the equation of f, you're going to times it by 3, which is going to give you x. And if you do g of f of x, same thing. G of 3x, if you put it into g, 3x over 3 is x. So, and you can see from here, if you input e into g, you get 1. You put 1 into f, you get 3. So you start at 3, end at 3. You start at 6, you end at 6. You start at 9, you end at 9. That's exactly what we're saying here. So any two functions that you swap x and y, and when you do the composite, nothing changes, are said to be inverses of each other. F and g are inverses of each other. So the notation we use for inverse of f, instead of writing all this, we write f to an exponent -1. Now, be careful. With variable x to a -1 exponent, it's 1 over x. But if you have a function to a negative exponent, it does not equal 1 over f. All what this means, it's the inverse of the function f. And how do we get the inverse? We swap x and y. Okay, that's exactly what inverse means. So for example, if I say if f of 1 equals 3, then, and I want you to finish this, f inverse of 3, right away you swap x and y, so you're going to get 1. 26, page 226. Part A, if f of 5 equals 18, then f inverse of 18 is 5. Swap x and y. Part B, if f inverse of 4 is 2, then f of 2 is 4. Okay, number 44, page 226. It says use the inverse function property to show that f and g are inverses of each other. 44, page 226. F of x equals x cubed plus 1. G of x equals x minus 1 to the 1/3. So use the inverse property. So what they want us to do is this. Find f of g of x and g of f of x. And they both have to equal x. Okay? So let's see if they do. So f of g of x, f of x minus 1 to the 1/3. And we're going to take x minus 1 to the 1/3 and plug it in for x right there. So it will be x minus 1 to the 1/3 for x, and then because of the cube, plus 1. 1/3 times 3 is 1. X minus 1 plus 1 is x, and that proves the first part. Here we're going to input f into g. F is x cubed plus 1. Input that into g, so we're going to take this and put it in there for x. So it will be x cubed plus 1. That's going to be plugged in for x, and then minus 1 to the power 1/3. X cubed to the 1/3, which is just x. So that proves that f and g are inverses of each other. There's another way of proving their inverses. It's less work, and I'm going to talk about this next. So given the equation of f, given the equation of function f, find the equation of f inverse. How do we do that? Now, let's be careful. If we're given ordered pairs, all you have to do to find the inverse, all you have to do is swap x and y. So given f is the ordered pairs 1, 2, 2, 4, 5, 3, its inverse right away would be 2, 1, 4, 2, and 3, 5, and that would be the end of it, as y and y is x. But if we're given the equation, how do we find the equation of the inverse? Well, the first thing is you have y equals f of x, so you're going to replace f of x with y. You need y in there, f of x or g of x or whatever it is with y. So you want to write it as y equal. Then remember what inverse means, switch x and y. Switch x and y, and then you want to isolate y. And now y is actually x because you switched x and y, and that y that you isolated is the inverse. So replace f of x with y, switch x and y, and isolate y. Okay, I just want to go back to the example that I did. Look, this example, number 44, remember how we proved that f and g are inverses? By doing f of g of x and g of f of x, and they both equal x. Now I'm going to do the same thing, showing that g is the inverse of f by following these 4 steps, okay? So I'm going to show you how to do that. So replace f of x with y. We did. Switch x and y, so it'd be x equals y cubed plus 1, and then isolate y. So we're going to minus x. And to get rid of the cube, we're going to cube root it. So y equals cube root of x minus 1, and that's the inverse. And that's exactly g of x, because g of x is x minus 1/3, which is cube root of x minus 1. It's an easier way to proving that two functions are inverses of each other. Okay? Here's another example. 48, page 226. You want us to show that these functions are inverses of each other. Look, I mean, we can rationalize that, right? Okay, if you look at f, it takes x minus 5, divide the whole thing by 3 times x plus 4. So, oh, it's gonna be easy. Okay, never mind, not for this one. So we're gonna start with f. We're gonna make it y equal, and then we're gonna show the inverse is this. Okay, y equals x plus 5 over 3x plus 4. So we wrote y equals f of x. Now we're gonna switch x and y. So it's x equals y minus 5 over 3y plus 4. Okay, so we have y's on top and bottom. Now we want to isolate y, so we have a fraction. We want to get rid of it first. So times by 3y plus 4. 3y plus 4. Distribute the x. 3xy plus 4x equals y minus 5. To isolate y, we want to move the y terms to one side and everything else to the other side. So we're going to add the 5 to move the 4x next to the 5. And then we're going to minus 3xy to move it next to the y. So we get y minus 3xy. So you can see I have the 4x and the 5 on this side. I moved this over here. I got y minus 3xy. Okay. Now we want to factor the y out to get it up. 1 minus 3x. And now we divide by 1 minus 3x. And that y is the inverse, which in this case is g of x. That proves that f and g are inverses of each other. Now I have an example on page 33 in the notes. I want you to go over that. Okay, so next one I want to do is 70, page 27. 70, page 227. Find the inverse function. So f of x equals square root of 4 minus x squared, where x is between 0 and 2. So this is for finding the inverse. Again, y equals square root of 4 minus x squared. Switch x and y. X equals square root of 4 minus y squared. Solve for y, so we're going to square both sides. We want to isolate y, so we're going to add y squared to move it over here. And then minus x squared. 4 minus x squared. When we square root, it's usually what? Plus and minus. But this time it's not going to be minus, because when x is between 0 and 2, y is between 0 and 2 also. Okay? Okay? So it can't be negative, so y equals square root of 4 minus x squared, and that's the inverse. Okay? Now, if we graph any function and we graph its inverse, the graph of f and the graph of f inverse are symmetrical, always. They are symmetrical along the line of symmetry y equals x. Why this line? Because remember, we get the inverse by switching x and y. If you look at just an example, just look at x cubed. Remember, we did f of x equals x cubed plus 1, and g of x was x minus 1 to the 1/3. I think that's what they were. Yeah. So if you graph these two on your grapher, I'll pull our graphers out. If you graph on your grapher, so y equals x cubed x to the power 3 plus 1, and then x minus 1 to the power 1/3. You graph these two functions, they're going to be symmetrical along the line y equals x. Actually, to make it clear, we're going to draw the line y equals x, and you can see how they're mirror images. So go to y equal, y2 equal, or y3 equals x, and then see how that fits perfectly as a mirror for these two graphs. Okay, so if you graph any function and its inverse on the same system of coordinates, they will be symmetrical with respect to the line y equals x. Okay, so if I give you this, if I say given number 72, page 227. F of x equals 16 minus x squared, where x is greater or equal to 0. Sketch the graph of f, use the graph of f to sketch the graph of the inverse, and then find the inverse. If you sketch the graph of f, it's negative x squared plus 16, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12, 13, 14, 15, 16. That's so when x is 0, y is 16. X is 1, y is 15. When x is 2, 16 minus 4 is 12. When x is 3, y is 7. So you can see how the graph shapes out. It's negative x squared plus 16, but it's all positive part. When x is 4, y is 0. Now, this is the graph of f of x equals 16 minus x squared. If you draw the line y equals x, it goes through 1, 1, 2, 2, 3, 3, 4, 4, so it's going to go like this. This is the line y equals x. Now if you do a reflection of this along the line equals x, so you take this piece, you're going to get take this piece, and then you're going to get that 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16. So 0, 16 would be 16, 0 on that. Remember we said 1, 15 will be 15, 1. 2, 12 would be 12, 2. 5, 6, 7, 8, 9, 10, 11, 12, 2, and so on. So you're going to have a graph. And then, so this piece is a reflection of this piece, and this piece is going to be reflected over here. And you get the graph of the inverse. And then they want us to find the inverse, so you do the steps. You write y equals 16 minus x squared, and then x squared is 16 minus y. X equals square root of 16 minus y. And there's no negative. So you can see that y is greater or equal to 0 in this case, okay? It's y is greater or equal to 0. Okay, so that's it for chapter. There's 96, just look at what I have in there, and that's it for chapter